In this video I will demonstrate how to perform a logistic regression, specifically a binary logistic regression. And this is a situation in which we have one or more explanatory variables. They could be either categorical or quantitative, and we're using them to predict a categorical or binary outcome. In other words, an outcome in which there's only two possibilities, such as pass, fail, has a disease, does not have a disease, survives, doesn't survive. So we can use that similar to the ways that we use multiple regression or linear regression, but now the outcome is categorical instead of potentially quantitative. So the data we're going to be looking at here is looking at passing or failing a certification exam. So this is data on healthcare professionals, and data was gathered on whether or not they passed or failed their certification exam on the first try. And then we have some predictive variables, explanatory variables we're going to use to try and predict pass or fail. So this was data that was collected during their time of their coursework. So we've got a clinical experience evaluation score. The higher, the better they did in their experience. There was an oral comprehensive exam, a written comprehensive exam, their overall GPA or grade point average, and then their grade point average within their major. We want to try and see if any of these variables then predict if the person is going to pass or fail their certification exam on the first attempt. Now, none of these variables are these explanatory variables are categorical. We could use categorical variables to help explain pass-fail, such as gender, geographic location. We could use that as well, but in this case we don't have any of those variables. We all have quantitative variables as our predictor variables. Okay, so in order to do the analysis, we first want to do a first kind of preliminary step is to actually look at the potential correlations between our predictor variables and our outcome to see if there is some kind of a relationship there, and that will give us some idea of what to expect as far as the strength of the prediction model that we come up with. And it will also give us some idea of which variables we may or may not want to include within the model. So we're going to go to Analyze, Correlate, and we're going to do bivariate correlations on all of these variables. So we've got our test result, a 0 being a failure of the test, a 1 being a pass. We've got an interview score that was an interview into their academic program. We have this clinical evaluation, oral and written comprehensive exam score, and then our two GPAs. And we're going to see how these relate to our outcome, our test pass or fail. So we make sure all those variables are entered in, and then we click OK. Okay, then we can go ahead and look at the test status and see how it correlates to some of these variables. And we can see that there are positive correlations to all of these variables. In other words, the higher the score on the predictor variable, the more likely they were to pass the exam. Remember, 1 being a pass score, 0 being fail. And these variables here at the end, the written comprehensive exam, the two GPAs, and the oral comprehensive exam score seem to have the best relationship with this outcome. So that to me indicates that these would be good potential predictor variables, as well as potentially the interview. The evaluation doesn't seem to be as strongly correlated, but we could still include that in our model potentially. So that's kind of a beginning first step, just get an idea of what variables appear to be predicting others. Now we could have negative correlations in these predictor variables. We could have a situation where a high value on one variable might predict someone more likely to fail on the exam, and sometimes we want to include those, but those tend to create what's known as a suppressive effect. In other words, it tends to kind of cancel out some of the predictive ability of maybe a variable that had a positive correlation. So those we have to be careful of because they can really affect how strong the model might be and how good of a prediction that model might then make. So let's go ahead and run the actual analysis then, now that we've done these preliminaries. So we go to the Analyze menu, Regression, and we choose Binary Logistic because, again, we're doing a binary outcome, and so we're going to choose that particular option. So we want to make sure our outcome variable is entered in the dependent variables box, and then we also want to make sure our potential predictor variables are entered into the covariates box. And the method we're going to use is known as the enter method, in which we're going to enter in all of the variables at once. We're going to enter them all into the model and see what kind of model they create. We can do hierarchical regression, in which we enter in variables in groups or one at a time to see how they might change the model. But that creates quite a bit more complexity in the analysis. So we're going to keep this fairly simple and do the enter method, in which we use all the variables simultaneously at the beginning. Now, if we happen to have a categorical predictor variable or explanatory variable, we would need to check this categorical box and then move that predictor variable over into the categorical covariates. And so SPSS can identify the fact that one of these, or maybe several of these explanatory variables, are actually categorical as well. So that is an element that would need to be addressed if we had that situation. Okay, we then want to go to the save option, and we want to ask for what the predicted group membership might be, so we can get an idea of how well this model is predicting someone's pass or fail on the exam. So we want to make sure that is checked. Click continue, and then we go to the options button, and we want to ask for this Hosmer-Lemmerschau goodness of fit test. This will give us an idea of how well our model fits the data. In other words, how well is it going to predict an outcome. And then we can also ask for the confidence intervals for the odds ratios that are going to be produced. We're going to get odds ratios produced to give us an idea of how likely someone is to pass or fail, depending on having a certain level of one of the predictor variables. And then this will also give us the 95% confidence intervals for those odds ratios, so we can report that kind of data, give us an idea of the magnitude or the clinical significance of our predictor model. Okay, once we've done that, we click continue, and then we click OK. Okay, so the first thing we'll see is how many cases were included in our analysis. We've got 92 cases. That's a relatively small sample size. A lot of the models tend to work better the larger the sample size. We have sample sizes in the hundreds, usually around 400 or so. Then that tends to be increase the likelihood we'll have a good model. But this is the data we have, so that's what we'll work with. The first thing we're going to see, or the first table we want to look at that's helpful to us to understand how good our model is this block 0, or beginning block. And this is basically like a null hypothesis. If there were no predictor variables available for us to make the prediction if someone were pass or fail, this is what the prediction would be, is there would be about 54 of the subjects out of the 92 would fail the test. And so without any possible predictor variables, we're almost kind of flipping a coin, saying there's going to be a 50-50 chance you're going to pass or fail. And so the overall model predictive ability is around 59% correct. So it's going to predict who's going to pass or fail around 59% of the time, without any predictor variables involved in the model. Okay, so that's kind of the null hypothesis. And so what's going to happen then is we're going to do a statistical test that's going to compare what our model with the explanatory variables is able to do compared to this null hypothesis. Presumably, if our model is a good model, it will be able to increase this percentage correct, hopefully close to 100%. Okay, the next thing we can look at are the variables that were not in the equation. In other words, all the variables that we chose as explanatory variables, if they weren't used in the model, this gives us an idea of how strongly they were able to create, or will be able to create, a significant model. So all of these variables, except for the eval variable, have a p-value less than 0.05. So that means that they're going to be significant predictors individually. They could individually have a good predictive ability for pass or fail. And so now we're going to see how they work together in our predictor model. So now we go to block 1, which again is where we've entered all the variables in simultaneously. And there's a couple things we can look at first. First is the omnibus test of the model coefficients. It looks at the model and compares it back to that null hypothesis that we had, and it produces a chi-square value. When the significance level for this comparison is less than 0.05, then that means we have a significant model, and that means the model will be a good predictor at a p-value of less than 0.05. So that's good news. That means our predictor variables are going to do a good job of making a pass-fail prediction. The next thing we can look at is the model summary here, and we have Nagle-Kirk's R squared. Now this is very similar to the R squared we used in linear regression, which gives us an idea of how much of the variance in the dependent variable is explained by our predictor variables. And here about 30% of the outcome, or 30% of the variance in the outcome, is being predicted by our predictor, or is being affected by our predictor variables. So that's decent. That's not, well, obviously we like it to be more, but that is a pretty decent number. About a third of the variance is explained by our predictors. The next test we can look at, or the next output we can look at, is this Hosmer-Leschamau test. And this gives us an idea, again, of how good our model is. And in this situation, we want the p-value to be greater than 0.05. If the p-value is greater than 0.05, then that indicates we have a good model. In other words, our model will be significant. If we had a p-value less than 0.05, then that would mean our model isn't very good. So that's, again, good news. That means we have a good model here. Now this contingency table related to this Hosmer and Leschamau test will give us an idea of how well, again, the model is predicting certain outcomes. And the outcome we're interested in is passing. Can we predict who's going to pass and who's not going to pass? And what this statistic does, it breaks the outcomes or the subjects up into groups, and then progressively tries to fit our model to the actual outcomes. And what we look at down here is the bottom. We look at this last step. And what it's showing here is that the observed number of passes in a group of subjects was 10, and our model predicted about 9 of those people actually passing. And so the closer these two numbers are together, the better the model is. So that's, again, showing we've got a pretty good model here, because we were able to predict about 9 out of every 10 people passing the exam that passed the exam, at least in these small groups of subjects, these small clusters of subjects. Now the next thing we can look at is the classification table, and this will tell us is how good our model was at predicting the actual outcomes. And so you can see here our model was able to predict about 69% of the categories. So almost 70% of the outcomes were correctly predicted by our model. So again, that's much better than the null hypothesis. The null hypothesis was 58%, and our model was able to predict almost 69%. If we can get our model into that 65 to 70, 75% range of correct predictions, that's a pretty good model. Obviously, the higher the better, but once we get above that 65% threshold, we think we're doing pretty well with the predictive ability. Okay, the next table we can look at, here's where we get the actual constants, the actual beta coefficients that we would use then to plug into our regression equation. So again, here's just like when we do linear regression, we get these beta coefficients and we use these to create our equation. So those, again, are useful to actually then be able to try and make a prediction with known values in these coefficients. What we also get here are odds ratios related to each of these variables. And so the higher this odds ratio is over 1, the more likely someone is to pass the exam if they have a high score. So for example, if someone has a high oral comprehensive score, they're about 1.1 times more likely to pass the exam. The one variable that seems to really have an effect on that is the GPA within their major. If they had a high GPA in their major, they're about 48% 8 times more likely to pass that certification exam. So that gives you an idea of kind of the magnitude of the effect that each of these variables might have on predicting the outcome. And then we have 95% confidence intervals for each of these odds ratios. Okay, so that concludes the video as far as how we do logistic regression. So to summarize, what we're doing with binary logistic regression is we've got a binary or dichotomous outcome. We can use multiple variables to try and predict that outcome. They could be categorical or numeric. We then attempt to create a regression model, and then we can look at various outputs. They then give us an idea of how good our model is in making the prediction. And then we're given some beta statistics as well as some odds ratios to give us an idea of how individual variables might make the prediction. And then we can use the beta constants to then actually construct our regression equation so that we can make predictions.